Alright, welcome to Air Science, video 3 of the day. Thanks for sticking with me. One thing I didn't mention back here on the last one, that isn't super relevant to the last one, but very important now, is this idea that continental crusts and oceanic crusts have some fundamental differences. And in these drawings, that as sloppy as they are, they're reasonably accurate. That's represented that's in the fact that these are thicker and these are thinner. You're also going to need to know, the reference tables gives you the relative densities of those. Sorry, I'm at a funny angle here. Continental crust at 2.7, oceanic crust at 3.0. Small difference, but when you're talking about things this massive, that racks up pretty quick. So the thinner stuff is more dense, the thicker stuff is less dense, which results in a balance, an isostatic balance within the mantle. But that's going to be important when they start running into each other. So now we're going to do convergent boundaries. We're going to do places where are the tectonic plates coming together. And we got 3 types we're going to do. OC, OO, CC. And all that stands for is oceanic to continental, oceanic to oceanic, which there's a lot of, oceanic to oceanic, and continental to continental. So it's really, if you just try to simplify, it's like what's the thing we're trying to do here? It's just what's on either side of the convergent boundary. There's ocean on this side, there's continental on this side, it's OC, right? And then we'll look at what kind of like landforms they make and call it good, call it Friday. So, oceanic to continental. What I'm going to need here is thin oceanic crust, as we discussed, which is going that way, moving that way. Thicker continental crust. And an ocean sitting on top of the oceanic crust. All right. There's a lot of these again, but let's do the textbook. The simplest example is what's going on over here on the west coast of South America. In the Pacific Ocean, this oceanic plate is heading that way, hitting South America, and maybe you know the name of that mountain chain that runs right through there. Here it is on your reference table. The Nazca plate hits the South American plate. There's the convergent boundary. So what happens is a couple of things. We mentioned density. Since this crust is more dense, it's going to subduct or sink. Let me give myself enough room here. I'm a smart guy. Sink down into the asthenosphere. Once it gets down there, I don't know, 100 kilometers deep, it starts to melt. And that hot magma, this is like a conveyor belt. It's always feeding new crust. It's always melting. And that heat that's generated from that, and as a result of that melting, makes these plumes of magma. They look like balloons, kind of. They melt their way up through the crust. And eventually, we call it lava. It comes popping out of the crust, and it builds a volcano. And then a bigger volcano. And then a bigger volcano. For years and years and years. There's also some like crunching of the crust here. You know, if I took this piece of paper and crunched it up, like you probably would at the end of class, if we were together, you know, it shortens it but thickens it, right? So that's what's going on here. The crust is getting squished. There's some folding and faulting through that, but there's also a lot of volcanism. If you find a volcanoes layer, I don't think I have it on here anymore. Or look at a volcano monitor, you'll see they're all over the place. There's eruptions through there frequently. All right, so oceanic, continental, if you didn't know, these are the Andes Mountains. And lo and behold, hey, if you want to do a little bit of rocks again, this is mafic, this is felsic, and when this mafic magma melts, goes through that felsic crust, you end up with an intermediate extrusive rock. I'll make you go look at your tables for this one. Can you think of an intermediate extrusive igneous rock that would make up the Andes? If you go look, it won't be a surprise. All right, there's one possibility. Sorry, noisy day in the Affinity household today. That's my water pump. Next one we'll do is Oceanic. which honestly is really the same thing. Oceanic, now instead of hitting a continent, goes underneath another oceanic crust. So oceanic crust, I guess the question is, well, how do you know which one's going to sink? It comes down to which one's more dense, which tends to be the older one, the one that's been around longer, because it had more chance to cool and compress, then it will be older and more dense. So really, here's what happens. Same deal. Only now I'm going to put an ocean right here. There's going to be some crunching in the crust there, no doubt. This mafic crust is going to melt. These magma plumes are going to rise right through that thin oceanic crust and form an underwater volcano. But keep that going, keep that going, keep that going. The volcano gets larger and gets larger and gets larger, and eventually comes poking right out of the ocean surface, giving you a volcanic island. Rather than a volcanic mountain chain, a volcanic island is the only difference here. So the Aleutian Islands, all volcanic islands as a result of this. Come down here. Don't worry about Hawaii. Just pass by Hawaii. Hawaii's a weirdo. We're not going to talk about Hawaii today. Same deal. We got a little ridge of volcanic islands through here as this oceanic crust goes underneath that oceanic crust. So there is OO. And again, there's lots of these. There, a lot of those islands. If you've heard of this idea of the Ring of Fire, the whole rim of the Pacific, with the exception of the San Andreas, tends to be a lot of convergence. So a lot of subduction and a lot of volcanoes and a lot of earthquakes. All right, lastly, let's do CC, which is, I don't know, maybe it's the easiest of the three. All right, India. India, until, boy, I'd have to check, but I'm thinking around 10 million years ago, don't quote me on that one, was a separate island tectonically. It was down here, and it was moving northward pretty darn quickly, in fact, and eventually, boom, slammed into Asia. And the result is the largest mountain chain that we presently have on Earth, right through here, the Himalayas. This has happened before in Earth's history. There's other old mountain ranges we have that are a result of this, but this is the today deal. We can use what we see today to analyze what's happened in the past. So they just really, here's all it is. They just really run into each other. Let's do this one like in phases. You'd have a continental crust called, that one day when humans evolved would say, this is called India. This is pre-human. And you'd have oceanic crust between them. And India is hauling that way. And there's a separate ocean between them. And yeah, if you're clever, you're probably knowing there's subduction going on here. There'd be some of that resulting in Asia, and there's absolutely evidence of that. You're right. That's the thing. And eventually when they hit, it's like a car wreck. When two things hit each other, these are both lower density, both buoyant. Neither one's going to be able to subduct because of that. They just slam into each other. And you get this big tall mountain range, which in fact also is deep. The result of this collision, you couldn't just have the mountains go that high up. They sink down into this mushy asthenosphere. So these are the thickest parts of the crust that we have right now. So tallest mountains and thickest crust, both. And that's continental to continental. All right, that was a lot. Thanks for sticking with me this far. I'll scan these notes and post them. I'll try to make the quiz as pretty straightforward as I can. And say good morning. Welcome to Earth Science. Happy Friday. Another week down, guys. Hope you're doing okay. I really do. Scary times. Stick with it. We're getting there. Email if you need anything, all right? We'll talk to you soon.